Yeah, our next speaker is Raquel, who has sent us a pre-recorded talk. So Raquel is a professor in the Department of Computer Science at the University of Toronto, a Canadian research chair in machine learning and computer vision, and a co-founder of the Vector Institute for AI. She recently launched Waabi, a company for self-driving technology.
Hi, everyone. My name is Raquel Urtasun, and I am the founder and CEO of Waabi. Today, I'm going to be talking about learning to drive in highly dynamic environments. Despite some meaningful progress since the DARPA challenge in 2004, there is still many things that remain elusive for self-driving vehicles to be able to do. In particular, there is like two main problems that still need research in order to be properly solved. On one side, we need to build autonomous systems that can solve the long tails of the distribution and all the potential rare events that might happen. On the other side, we need real-time high-fidelity simulators that enable us to be able to test at the scale both common scenarios as well as safety-critical cases. At Waabi, we are approaching this with new technology. In particular, we have an AI-first approach to perform the brain of the self-driving vehicle, which produces intermediate interpretable representations and enable us to basically explain the decision-making of our system. Furthermore, through complex reasoning, we can solve the long tails and generalize to new geographies much faster than existing approaches. We also have a novel closed-loop simulator with an unprecedented level of fidelity that allows us to test at the scale both safety-critical situations as well as common scenarios. As a consequence, we don't depend on driving millions of miles in the real world, and instead we can learn directly from simulation in a way that correlates nearly perfectly with the real world. We are starting with a use case of long-haul trucking because there is a chronic shortage of drivers, as well as there is pervasive safety issues that this technology can definitely help tremendously. The super exciting news is that we launched the company only a week ago, and it's been super well received. We have a backup from an incredible set of investors, which are best in class in terms of deep technology, logistics, as well as the thriving Canadian ecosystem. We have offices in both Toronto as well as San Francisco, and we are actively hiring. So please come to our webpage where we have many openings for you to apply. If you are interested in changing the world through self-driving, please, this is the moment for you. Now let's get back to the topic of the workshop. And let me start by explaining how a self-driving system works. First, the vehicle senses the environment, which is illustrated here with the LiDAR point cloud seen from the top. Then we typically localize with precision of a few centimeters such that high-definition maps can be used. Then the perception system perceives the objects around it, and the prediction system basically forecasts the trajectories of where potentially the different actors might be in the next few seconds. This is used by the motion planning module in order to predict, to plan a safe maneuver that basically gets executed. And this process is repeated every fraction of a second, typically every time there is a new observation. Now, if you look back at the problem of perceiving the world and predicting what the different actors are going to be doing, there is a few main challenges that remain open. First, the world is basically multimodal. So this is illustrated with this picture here, where we have a vehicle that is entering an intersection, and it could be that this vehicle continues straight or actually turns at the intersection. And typically, there is no way to know in advance which one of these scenarios is going to happen. Furthermore, it's not that every actor basically acts independently. Instead, there is interactions between the different actors. For example, here are two actors that are interested in turning at the intersection. However, they're going to be interacted such that these maneuvers do not result in collision. The other difficulty of doing prediction is, or in general doing autonomy, is that we have very stringent constraints in terms of the latency of the system. And in particular, our reaction time is super important for safety. So we need to do all the computation in a fraction of a second. So it doesn't really matter how good your model is if it doesn't, if it's not able to do this process in a fraction of a second. In order to handle multimodality, there is many approaches that have been proposed. From the use of a mixture of Gaussians, which is a very natural way, to occupancy grids, where basically you can represent the distribution of where the actors might be going in a non-parametric way, or in terms of a specific set of trajectories that are caused in order to create a probability distribution over that discrete set, or autoregressive models that basically you can sample on the first frame and then unroll the prediction into the future. Typically, these models make a trade-off between the specificity of the model as well as the complexity in terms of memory and time consumption in terms of the prediction. Now, if you look at the literature, all these models look at multimodal distributions for every actor, but basically they model the marginal distribution of every actor. And this is problematic. And the reason why is that it's actually pretty difficult for a motion planner to use this information. So let's look at an example. So if we actually model the marginal distribution for every one of the actors in the scene, what's going to happen is that in order to plan a safe maneuver, typically what a motion planner does is that it samples every one of these marginal distributions. So we're going to end up with a set of trajectories for every one of these actors. And then given all this set of trajectories, then it basically needs to decide what to do. Now, what's going to happen is that in order to not enter a collision, typically one uses a worst case scenario planning and then ends up with a situation where the planner is super, super conservative and it doesn't advance much. However, if you actually look at what's happening in reality, is that not all this, the cross product of all these samples are actually feasible. Instead, there is a lot of correlations, right, between how the actors act together. Right, it could be that the different actors are actually yielding to us, and then a plan that would make sense would be to go straight, maybe even accelerate, or it might be that they actually decide to, cut in front of us and then turn on the intersection, and in that case, we want to slow down to not enter a collision. Right, so there is a smaller set of possibilities compared to the cross product of all the samples from every single independent actor. So in order to do this, we need to model the distribution of the scene, of the joint scene. So let's look at how we can actually do this. So what I'm going to show you next is how we can go all the way from perception to action by first perceiving the environment, then predicting a joint distribution over the behaviors of all the actors in the scene in a way that is consistent. Then I'm going to show you how to sample diverse samples so that we can very efficiently take into account the possible unrolls of the scene. We're going to see how we can score the probability distribution over all those joint samples. And then finally, I'm going to show you a contingency planner that is able to drive very safely, but at the same time, not be super conservative, as you will see with traditional planners. All right, so let's start with perceiving the world. So how can we do this? We're going to start with the raw sensor data. In this case, illustrated with the LiDAR, but you can use more sensors as you wish to. And then we are also going to have a representation of the map. And this can be a raster or can be some graph representation, which we have also done in the past. Then we're going to have a neural network that basically is going to fuse this information. It's going to create some intermediate representations from which we're going to do object detection. And in order to have very precise bounding boxes and be able to predict nicely the future, we are going to basically, through an operation of ROI align, we are going to extract meaningful features from which to make these predictions. Okay, we're going to collapse this in terms of the observation variable X. All right, so now that we know how to detect objects in the scene in a way that is very reliable, let's look at how we can actually model the joint distribution of all the actors, how they will behave in the future. So we're going to do this through a latent variable model. In particular, it's a conditional latent variable model, which is a generalization of a conditional VAE, where both the encoder and the decoder are going to be graph neural networks. And this is very amenable to our problem because we have a variable number of actors, and this is a way to take into account their interactions. Okay, so the encoded will be through a graph neural network to the latent variable. right? And then the decoding would simply be, again, message passing through the graph neural net, so a different graph neural network to decode into the different trajectories for all the actors in the scene. So how does this work? We're gonna do, in terms of inference, we are gonna do a forward pass to basically do detection and compute the features for the different actors. Then we're gonna encode in order to sample from the distribution. Then given a particular sample, we're gonna decode through the graph neural network and create, given one sample, we create the unrolling of the entire scene into the future. Okay, so instead of traditional methods that is a single actor, now we unroll the entire scene with a single sample. All right, and we can do multiple samples, and then we will have different realizations of the scene. So what I'm showing you here is for every one of these videos, basically we sample 2 samples from the latent space, and then we're going to interpolate in between, and we're going to decode. Okay, and then this is to show how smoothly you can, as you traverse the latent space, you basically change the distribution of the motion of all the actors. So this is where we are modeling the joint distribution of everybody that is in the scene. So you can train this model end to end, and you can do this by using a variation of you know, how you will train a conditional VAE, where basically we are going to have a loss function for the detection. We're also going to have the KL loss in terms of you know, matching the distribution of the privilege posterior with respect to the prior. And then basically we also have a reconstruction loss that tell us that we should actually have realizations that look like what happened in reality in our training set. So this model actually works really, really well. And importantly, if you look at, you know, the state of the art in terms of prediction, it actually works much better in terms of how many of these predictions actually collide. It's much more socially compliant. So the lower, the better, right? And also works much better in terms of, you know, how well it mimics what actually humans do, the particular scenes that form the test set. Now, if you look at the model itself, so it works really, really nicely, as you can see here, where different timestamps are in different colors. But one of the things that, you know, to notice is that it does really well in metrics. However, so it achieves very good reconstruction. However, it doesn't use multimodality very often. And that's not necessarily something that we want when we're interested in motion planning, right? We would like to be able to take into account all the possible realizations of the scene such that we are able to potentially react to those in the event that they actually happen in practice. So what we're going to see next is how we can modify the sampling mechanism utilizing this model to have diverse samples. Now, if you look at the literature, typical models, you know, when you sample from them, they're very sample inefficient. Particularly for low probability modes, you have to sample many, many, many times to actually get one sample of that realization. There has been recent approaches that look at how can we utilize diversity to learn better sampling mechanism. The problem here is that diversity is typically in terms of just the trajectories of the actors in the scene. And that's not necessarily the right measure of diversity. Instead, what we propose and what we use is a measure of diversity with respect to our motion planning, right? So we would like to be super sample efficient, meaning that the samples of the realization of the scenes should be such that they actually result in different planning maneuvers for the self-driving vehicle, right? And this is the way that you can really, with a few samples, you can take into account all the possible behaviors that you might need to do. So in particular, we have a way to you know, learn to sample through a GNN, where with a single sample now, we're gonna not only sample entire realizations of the scene, but we will sample key realizations of the entire scene. Okay. And what is important is that we will, you know, we will get coverage with only a few samples. So the next thing that we need to do is basically, since we have a different sampling procedure, we need some notion of likelihood of every one of our samples. So the way that we actually do this is just by learning a scoring function, which is going to be normalized to be a probability. And we do this such as the actual realization that happened in practice in the dataset is actually high probability. Okay, so we basically just minimize the KLD variance between a smooth version of the label of the ground truth and our samples. Lastly, now that we have a way to have diverse samples of entire realizations of the scene, we need to be able to use this for motion planner. Right? So typically, when you see prediction papers, they stop here, but they don't really discuss into how can you actually employ these multimodal distributions, typically, as I said, marginal distributions. So what we're going to look next is how we can build a motion planner that can really exploit nicely these probability distributions of realizations. And first, I'm going to explain why we need to do something better than what exists out there. So if you look at the typical planners in the literature, so the way that they will work is that for every time that you receive an observation, they will plan an entire trajectory, typically for 8 to 10 seconds. Okay, and there is a problem with this, which is the following, right? When you have multiple realizations of how the future might unroll, what happens is that if for example you have in this case this particular trajectory that you're trying to evaluate how good it is, there will be one realization of the scene in particular where they are actually not yielding to you, where basically you will collide, right? So as a consequence, you will end up with solutions for this worst case type of planner where basically are super conservative, because you need to make sure that whatever you plan for the 10 seconds will never collide with any possible sample into the future. So this is why typically you see self-driving vehicles that are very, very slow and that you don't really behave like humans. So what we're going to look at then now is how we can build a planner that is safe, but at the same time is not so conservative. And the idea is actually very simple, which is the following. These planners are model predictive controllers, which means that every time that you get new observations, you actually replan, right? This typically is every 100 milliseconds or so, right? So if you think about it, you don't need to plan a single trajectory for such a long horizon like 10 seconds, because you're going to be replanning, as you drive. So basically, we're going to build what is called a contingency planner, where we're going to build a short-term trajectory that no matter what happens into the future is going to be safe. And then we're going to basically build a different solution in terms of the trajectory for every possible realization of the future of the entire scene. Right? So this is basically saying that I'm going to execute this trajectory in the short term no matter what, but in the future I can actually react and then do different trajectories because I have enough time. And what I want is that the short-term trajectory such that no matter what happens in the future, I will be safe. Right? So this is the idea of this contingency planning. All right, so the way that we do this is that we sample many, many trajectories. Then for every one of these trajectories for the short term, we sample many, many long-term trajectories. And the trick is really into how you actually cost these trajectories here in order to select the best short-term trajectory. Okay, so let's see how we can do this. So in the short term, as I said, we want to make sure that we are always safe. So this is sort of a worst case planner. Is no matter what happens in all these samples of the realization of the short-term future, I minimize the danger that I will have. However, for the cost to go, which is from this small trajectory to the actual long-term trajectory, I can do something different, which is that for every realization yi of the entire scene into the future, I'm going to have a different trajectory for my motion plan. And I'm going to select the trajectory that is actually safe for that particular realization. And this cost to go, basically, the way that I compute it is that I weight these realizations, these plans for the different realizations by this likelihood function that we were actually costing before. Okay, and this is the way that I can have a cost to go where I'm going to be safe no matter what happens after. And the cost that we use here is a combination of safety, progress, and comfort. The typical cost that everybody will will utilize in motion planning. So just visually, what this does is, so here is a scene. So let's say that the short-term trajectory that we choose is actually to continue cruising. So what happens is that if these actors decide to yield to me, which is one realization of the future, then I can continue, or maybe even speed up a bit into the future. However, if they decide to cross the intersection, right, and don't wait for me to pass, then I will actually need to slam on the brakes, right? So what this means is that the cost to go here is going to be very, very high, right? Because I need to slam on the brakes, and that drives up the cost to go. So this trajectory is actually pretty unsafe. So this will not be a trajectory that will be selected by our contingency planner. Let's look at a different type of trajectory. So maybe what we're going to do is slow down slightly. Okay, and if they yield to us, I can always continue, and accelerate. And if they decide to cross and pass in front of me, then basically I can smoothly react, right, and maybe brake a little bit. Right, this is a much better trajectory because no matter what happens in the future, I can actually react to it. So this will be sort of the trajectory that will be selected by the contingency planner. So we're going to evaluate this in a closed loop simulation system that is, is all the way to utilizing sensor simulation, as you can see here. And we're going to create many safety critical cases, okay, so that we can evaluate how good this motion planner is. And it's very, very important that for motion planner, we don't evaluate just open loop metrics, because open loop metrics really do not tell us much about how good a motion planner is. Instead, we need to do this in a reactive manner where we really understand whether there's any compound errors. Okay, so we are going to basically have a system that at every time step, basically the autonomous system is going to react. It's going to move. The actors are also going to be reactive. We're going to update the world state, and we're going to resimulate how the sensors we have observed the scene in the next frame. And then again, we pass through the autonomy system. Okay, and we do this at 10 Hz, which is the typical frequency of the LiDAR, which autonomy systems actually utilize. So in terms of metrics in closed loop, this actually works really, really well. This is in terms of percentage of collisions in these super, super challenging scenarios. So we see that compared to other prediction plus planning methods, we do much better. Yes, for comparison, this is multipath is basically the Waymo system. So we are much safer. We can actually progress much more before potentially we get into trouble. And in general, we have much less, we have much better comfort. And what is interesting is that this contingency planner likes to do things like, avoiding obstacles or changing lanes, which is something that is typically really hard to do with traditional planners. And it's actually a good thing that we actually have this lateral acceleration. So it's great to see that the contingency planner is able to do this avoiding maneuvers in the situation of an event that something dangerous is going to happen.
In closed loop simulation, the SDV is at the center in green, and the other vehicles and their trajectories in blue, and finally the pedestrians in pink. Let's focus on the diverse predictions and response from the planner. The short-term action planned in the SDV is plotted in black, and the contingent trajectories are plotted in different colors, which in this case accounts for the variations in the speed profile of the left-turning car. As you can see, the SUV passes the intersection safely and cruises smoothly. In this scenario, the SDV plans different accelerating trajectories to be safe to unlikely samples from oncoming traffic coming into our lane, and successfully goes across the intersection. Here, our model avoids the hard brake before making the left turn by planning safe contingent trajectories to the diverse speed profiles from oncoming traffic, and smoothly effectuates an unprotected left turn in this fast-moving scenario. Here, the car in front of the SUV might turn or go straight, and thus it might potentially brake before turning. The SUV plans both cruising and braking trajectories to safely account for that, and it comfortably drives through the intersection. Finally, we show that our planner can stay patient and avoid a swerve even when there are predictions coming at it, but there's still time to react.
All right, so that's for qualitative results. So just to conclude, we show that modeling the joint distribution of the entire scene is actually important instead of modeling the marginal distribution of every actor independently, we show that we can cover all possible futures with a very, very few samples by looking at diversity in terms of motion planning. And we show a contingency planner that is much less conservative than traditional planners and result in safer maneuvers. If you are excited about changing the world with self-driving, come and join us. This is all for me today. Thank you.
Your recorded talk. So now Raquel's here to take questions from the audience for maybe like 5 to 10 minutes. So if there's any questions from the audience, feel free to unmute or type questions in the chat. I'll give you guys a couple of seconds.
I have a quick question. Thank you, Raquel, for the very nice presentation. You mentioned latency as a key factor in the beginning of your talk. I was curious how latency played a role in these benchmarks that you presented towards the end of your talk.
Yeah, so I mean, good question. So we are not necessarily benchmarking latency in what in the results that I'm showing you here. Instead, we are focusing on can you drive safely. Now, one thing is a research paper and you can show. Another thing is when you actually translate this into the production software stack, right? And there is a lot of work that goes into customized operations and other stuff, right? Mixed precision, blah, 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 such that, this system that runs, in say 100 milliseconds actually runs in say 30 milliseconds or so. Yeah, so for the purpose of, I guess, the academic version, I'm focusing here on the, simply the modeling aspect, as well as sort of the importance of the closed loop simulator. But great question, definitely is something that, I wanted to mention that this is actually something to take into account, because oftentimes we see methods that actually take seconds to do inference instead of say on the 100 milliseconds, and then it's impossible to translate that into a real production system.
I guess I have a quick question. I was wondering, so like the work in Lookout was really cool. And I was wondering, what are some of the future steps that you see needs to be done to like in the next stage of self-driving?
Yeah. So there's plenty, right? But there is like really two main things to solve. The first one is, having an autonomous system that is able to really handle on the long tail of the, distribution of events and things that might happen. And there is some open questions on this. For example, how do you handle things that you don't know what they are? How, can you generalize really to totally different geographies? In the context of Waabi, we are interested in self-driving trucks, so we need to see much further and plan for a much longer horizon. And then computationally, that's challenging. So, how can you do that? And what kind of new models do you need in order to do this? From the planning perspective, something that we are very, very interested in is what is the best way to train end-to-end, the entire software stack, right? And one of the remaining open questions is, what is the right metric for self-driving? The industry uses miles per intervention, but the metric is bogus, as everybody in the industry knows about. So instead, right, how can we measure success? How can we measure progress in a way that really give us the right signal for advancing self-driving? So that's one of the open questions. And once you know the metric, then you can optimize for it, right? So whether you find a differentiable version of it, which would be, you do supervised learning, or whether you use a REL and then it doesn't matter about differentiability, right? So that's, another open question. So that's with respect to autonomy, some of the, key aspects. And in particular for us, we look at end-to-end systems, but they are explainable, interpretable, that you can verify, right? And that's sort of the direction that we've been doing in the past, N years, but we're definitely pushing further. And the second aspect is as it relates to simulation, right? So in the industry, we see that, people claim to do a lot of simulation, but what they really mean is that they only simulate actors and their behaviors, and the actors are typically bounding boxes, right? And that only tests motion planning. And the input is not only the distribution of mistakes and issues that you will see in perception and prediction, right? So instead, what we're trying to do is, or what we're doing is a closed loop simulation, real time, with sensor simulation, like super, super accurate. right? And there is many underlying questions into how do you model behaviors? How do you get these assets automatically from the real world? How do you know whether you cover the entire spectrum of things that might happen versus not, etc. So there is still so many open problems. While we are talking here, we're actually giving a full day tutorial today where we're actually going over the entire sort of software stack in self-driving and sort of talking about some of these remaining open questions. Yeah, sorry for the long answer to your question.
Oh no, it's very helpful. Thanks a lot. We are running a little bit behind, but I just had a very quick follow-up on the metrics question. So like, how does one begin designing metrics that measure things like comfort, like of the driver? Like that seems very difficult.
Yeah. I mean, you can measure comfort, and there's many ways to measure this, right? Just by looking at derivatives, things like jerk, etc. You can, look at some safety as it relates to collision, but safety is more than just collision, right? You can look at things like how much you progress in terms of, is your self-driving car too slow and too conservative, right? But at the end of the day, you would like to have somehow a combination of these metrics into a single number that you use to make decisions into, is the system better than what I had yesterday? Yeah, where I am with respect to, where I'm supposed to be, etc. Right? So that's, one of the open questions in self-driving, and once you crank that, you will be much farther along than otherwise.
Yeah, thanks a lot. And thanks for joining us today.
My pleasure.